Okay, we had two homework questions I asked you, and I have redrawn it already. So there is the first question, where you were asked to draw the shear force bending moment diagram, and sketch the deflected shape. Before, of course, we can do that, we need to calculate reactions. So looking at this problem here, you would, of course, start the problem saying, okay, I have 2 pin supports, 4 unknown reactions, but I'm not going to panic because I have an internal pin in there, and I know what that means is, in order for me to calculate reactions, I need to split it at the pin. So we need to consider 2 free body diagrams, one here and one there. So looking at those 2 free body diagrams, well, I haven't drawn the whole free body diagram, just the structure there. Which side would you think you would like to start at? AC or CB? Yeah, I'd give AC a go. It's horizontal. We have a load, 10 kilonewtons per metre. Our member is 4 metres long. So tell me, what are these 2 reactions equal to? Some symmetrical loading, symmetrical structure. Each of these reactions here is equal to 20 kilonewton. So I have an up force 20 there, a down force 20 here, and thus over here, what's my up force? 20. So we've now solved for 2 of our reactions, our vertical reactions. So what I haven't put in yet is this horizontal and that horizontal, and a horizontal here and a horizontal here. So over here, this one's AX and this one's BX. Now I want you to look closely at member BC. So member BC has a pin at both ends, and it has no load. No load applied along its length. So if you look at member AC, it has a lateral load, so we know it's going to bend. So drawing the deflected shape now. Member CB, there's no load being applied directly to it. So because it has a pin at both ends and it has no load. What am I writing? Loaded. Hang on. And it has no, and I didn't need to rub the whole thing out, did I? And it has no load applied along its length. What does it mean? It means, therefore, the internal action in this beam is axial only. So this member, it's like me holding my pen with 2 pin ends, okay? If I try and apply a force that's not in line with the member, it will move down. So thus the only load this member can carry is an axial load. So if we go back to our member orientation here, it is 3 metres high and 4 metres across, so this is our good old 3-4-5 triangle. So you can either consider it as a 3-4-5 triangle, or note that that angle in there is 36.86 degrees, and that's just through some trig. So if we know the value of by, which we do know, it's 20, we can very quickly work out the value of bx. So you can either consider this to be a method of joints, so to speak, where we can call this force BC. We know that force is 20. We call this bx. I've drawn my free body diagram of my joint. It's in equilibrium. So thus, because I know that angle in there, I can work out what BC is, because all the forces in the x direction equal 0, and all the forces in the y direction equal 0. and I can work out the two forces. The other way to look at it is to say I'm going to draw my arrows top to tail, so Bx and this 20 kilonewton must add up to my resultant FBC. So thus, this Bx force must be pointing to the left. And based on knowing that angle in there, I can say tan of 36.86 degrees is equal to 20 on Bx. So either method will give you a Bx force equal to 26.67 kilonewtons. So however you choose to look at it. The other way you could look at it, as an alternative now, I'll go back to another pen colour that's easier to read. Okay, I can base on these free body diagrams. Why don't I take moments at C? And taking moments at C, we know that some of the moments have to equal 0 because it's in equilibrium. So I would say my 20 kilonewton vertical load times my horizontal distance of 4 gives me an anti-clockwise moment about C. And then as drawn, I have my Bx times its perpendicular distance 3 metres, and that's also plus, equals 0. So from this, Bx is equal to minus 20 times 4 on 3, which is equal to minus 26.67 kilonewtons. So I have a minus sign this side this time because my arrow is going in the opposite direction. Oh, I should have really put it, well, I left the minus sign out here because I was working on that basis and I'd already rotated it round. So the important thing to note here is just that you recognise member BC is effectively like a truss member, it only carries axial load. Okay, so knowing that, deflected shape. As drawn here, our horizontal member will deflect down. Member BC, it won't experience any bending, it will shorten, but you can't see that in this deflected shape. Okay, so now we draw the shear force diagram. So what did we say our reactions were? We said that's 20, that's 20. I worked out that that was 26.67, so therefore my reaction at A is also 26.67. So when it comes to drawing my shear force diagram, I stepped up a value of 20. My load reduced linearly, a total of 40. And when I did split it here, you saw we had a reaction of 20, so it steps up. Because what is shear force? We say it's a plot of the vertical force on a horizontal beam. It's actually a plot of the force perpendicular to the axis of the beam. And we have agreed that our member, well, I have told you, and hopefully you can see, that our member BC only carries axial load, so there's no shear in that member. So there's my shear force diagram, and thus my corresponding bending moment diagram here. Well, simply, we have a positive shear force, it's a downward slope, a negative shear force, it's an upward slope. My bending moment at my pin support is 0, my bending moment at my internal pin is 0. So because my shear force is linear, my bending moment is a parabola. So there's my bending moment diagram. In terms of the value here, that area in here will give you the value of the moment here, area 1, which is equal to 20 times 2 metres divided by 2, which is 20 kilonewton metres. Did people who did it at home get that? Yeah? Well done. So it's a simple one. It's a question that initially you go, oh my God, what am I going to do? It's forces at angles. And the shear force bending moment diagram is very simple. So the load is being transferred through member AC here in bending and shear. The structural action in member AC is bending and shear. The structural action in BC is axial loading. So that was a fairly easy one. With this one here, to those 5 that did it, I apologise. What I'm going to do now is I'm going to give you guys some reactions, and I want you to attempt to draw the shear force bending moment diagram. So our horizontal reaction at A must of course oppose the horizontal action acting of 30. My vertical reaction at A must of course oppose my action of 20. And when we do take moments, it's a very wonky moment, but that moment as drawn in there, I've actually drawn it the wrong way because in actual fact it is going the other way. My bending moment, which you can work out yourself, I'll give it a positive value and draw it in the direction it's acting in, is 50 going clockwise. So, could I have an attempt at a shear force and a bending moment diagram? Remember when we look at these, the vertical members, you have to decide where you're looking at it from. So assume your eye to pupilled. Ooh, love how it pupilled eyeball. So assume you're looking at it that way and have a go at drawing your shear force and your bending moment diagrams. Please. Now while you're doing that, I also brought my model of my corner that I forgot to bring last week, just to show if I have a load down, I said you'll either have an inner where you get tension on the outside, or if I apply my load up, an outer corner where you get tension on the inside, of both. So you'll only get your corner doing that or that. The only time you would get tension on one side and tension on the outside is if we apply a moment at that corner, and I won't do that to you. So when it comes to drawing your bending moment diagram, we draw it on the side that's in tension. So your bending moment will be on the inside of this vertical face when I push up, and it will be in the inside of the horizontal face when I push up. If I push down here, you can see the top is in tension and the right is in tension. So my bending moment will be up above and it will be on the outside. So the value of the bending moment here will equal the same as the vertical horizontal value of moment. And I said you can imagine that we flatten this out. So whatever moment you get here is the same as the moment you get here. Whatever moment you get in there is the same as the moment there. Okay, shear force diagram is relatively easy. The way I've drawn the eye means I'm looking at it from the right. So you start at the left-hand end, so the bottom would be the left-hand end. I step down a value of 30. There's no load change, I step up. And what brings it back to 0 here is this horizontal load. Now when I draw the shear force diagram in the horizontal part of the structure, I step up a value of 20, I move across, and then I step down 20. So moving across to your bending moment diagram, a positive shear force we say is a downward slope, And when we look at the vertical face, a negative shear force is an upward slope. Now, because my shear forces are constants, your bending moment will be linear. Your bending moment is just a result of a single point load times a distance, force times distance. So what's the bending moment at the cantilever tip? Oops. Everyone, together, 0. What's the bending moment at the fixed support? What's the absolute value there? 50, okay? You know it's equal to the bending moment in the beam. If I now draw a small free body diagram here, I'm saying the moment in my reaction moment is 50 clockwise. So to get equilibrium, the moment in my beam, 1 mil up, 0.1 mil up, okay, would be an equal and opposite 50. Which side of my beam is now in tension when you apply that moment? Yeah, the right side. So thus, we plot our bending moment on the tension side of the beam. So that means that moment in here has a value of 50. So now you can simply join the dots. So if it's 0 up here at the tip and it has to slope up in a linear fashion, the only thing it can do is that. Now if I look at a free body diagram of that corner there, I'm saying my bending moment is on the outside. That means tension is on the top. So my moment must be hogging. Yeah? So the moment here to get equilibrium must be drawn anti-clockwise. So going round a corner, I have tension on the outside, on the top, tension on the outside. So this is my tension side, so going round a corner, those two values are equal. So as I said, your bending moments are both either on the outside or both on the inside. And then we have a straight line here joining them up. So we have one value left to calculate. That's the moment in the corner. What's the value of that moment? Very quickly, I cut the beam here. I cut the beam here. What's that moment equal to? 20 times 2 metres. So 40. Does that make sense? I'm cutting it. Here's my free body diagrams. I'm cutting it at 2 metres. I want to know what the moment in the corner is. So that moment there is 40 kilonewton metres. That moment here is 40 kilonewton metres. So now, based on that, we can attempt to draw a deflected shape. Have a go at the deflected shape. Now, in saying have a go, you know which side of the beam is in tension. Down here, from my bending moment diagram, because I draw it on the tension side, I have tension on the right, then I have tension on the left, and I have tension on the top. So what corresponds in my deflected shape to moment equal to 0? Yep, occurs where you have a point of inflection. So, how do you think this thing is deflecting? In order to, we know at a fixed support there's no initial rotation, so we have to draw it effectively vertical. But to have tension on that side, it must be moving to the left. And now I'm going to, this is exaggerating, now I'm going to draw a point of inflection. About there. And my corner here is what I call an inner. It stays at 90 degrees, but I've got tension on the top. So, is this hard? Yeah, when you initially see it. But are there set rules you just have to memorise and learn to apply. And when you do enough of these things, it will become second nature. So there are rules, you just have to learn them. Now one more thing I just want to mention before we move on. So I will move the slide along. And that is, sorry. Any questions about that? Okay. One is, no, I want black. Where's damn black? No, it's not giving me black. Remember I mentioned we can use superposition. So if I do consider these two cases separately, a 20 down plus a 30 to the left, dealing with this 30 to the left first, I have a 30 here, a 30 here. Do I have any horizontal force? No. So if I attempt to draw my shear force diagram here, I won't do it with numbers, I'll leave you to do that yourself. But shear force diagram here, there's no shear force in the vertical leg, and then you step up and across and down. No, I've done it the wrong way around. When were you going to point that out to me? Okay, so the shear force diagram is down and across and up. Have I got any bending happening in the horizontal part of the beam? Is there any curvature? Is there anything happening? No. So the bending moment diagram is simply equal to 30 times 3 metres, which is 90. That will give me a moment here of 90 kilonewton metres. And now, when I consider the effect of the vertical load, I will leave you again to work out these bending moment shear force diagrams yourself. However, that is 20, so when I draw the shear force diagram this time, I step up, across and down. So my my bending moment diagram this time, it's 0 at the tip, it has a value here. Now the bending moment can't just disappear, it goes around a corner. But because I have no shear force, it must be constant through here. So when you look at the bending moment we got on the other page, it was a sum of bending moment diagram 1 and bending moment diagram 2. So if I add them up, I come up like so, going around the corner, one is constant and one is reducing, so that will give me that combined bending moment diagram that we got before. Okay? So, look at this in your own time. You have a lot of it. Well, I mean, there's no point in me going on and on about it here. So you should have looked at this already, so have a look at it. Okay, moving on. So we moved on to shear. No, bending stresses. So I'll just very quickly go over what we've done already. For trusses, we know because our forces were only axial, when we applied our internal forces, that gave us a uniform stress distribution. And that stress distribution was simply P on our cross-sectional area A. With our bending moments, and I brought my other bit of foam, carried it across, things now bend. And hopefully even people at the back can see the bottom is stretching and the top is squashing. So we no longer have a uniform stress distribution. Here's the man doing it, but don't I do it much nicer than the man? Okay. As I said, small things amuse small minds. I have to keep myself happy. We get that curved shape, and thus our stress distribution is no longer uniform, but it's linear. We assume it to be linear, it's linear elastic. So in this case here with a downward load you would get tension stresses in the bottom and compression stresses in the top. So what I then ran through at the end of last lecture was the proof of the formula. So I won't go over all of that again, but what we ended up with, and you can follow the proof, and if you have any difficulty you can come and see me, was we ended up with a relationship between moment and curvature, and then I went further and I came up with this wonderful formula, which is the formula you need to know how to use. Shh. This is the formula for bending stress. Now please don't be confused. I may ask you what the tensile stress is. You have to recognise it's bending stress we're talking about, and it's the tensile bending stress formula you need to use. If your beam is bending, if it's curving, it's the bending stress formula. Please don't get a bending moment diagram and find your vertical reactions and somehow magically turn them into horizontal reactions and a compression force on your member. It takes a lot of imagination to do that. Now, in our formula here, this is the relationship between our bending stress, our bending moment, I, our moment of inertia, which we'll spend time on Wednesday. This I is a geometric property. Thus, it has a constant value for a particular beam. So I'll show you how to calculate I. The variable in this equation is y. Y is our change in value. So this is the equation for this linear distribution line. So this is something that people don't understand. Y is the distance from the neutral axis. So when I am sitting at the centroid of the section and I bend it, my beam, because this is a symmetrical beam, at the middle of this beam, there's actually no stress in the beam. It's not stretching, it's not squashing. And that's what we call the neutral axis. So, at the centroid of the beam here, because y is measured from the neutral axis, at the neutral axis, y is 0. And thus, our bending stress is 0. So where is your stress maximum? Where y is maximum. And where is that? At the top and or the bottom of the section. So, if I asked you, I'm going to put a point load on my beam, okay, where is the bending stress maximum? You would draw a bending moment diagram to work out where your moment was maximum, and then you would know it was at the top and the bottom of the beam. So you couldn't just say in the middle of the beam, you would say my moment is maximum in the middle of the beam when I push down with my chin and look like an idiot, yeah? My moment's maximum in the middle, the bending stress is maximum in the middle, at the top and the bottom. So just be very clear that this formula here is effectively stress is equal to Kx, or I know I should call it Ky. And this K is a constant here, equal to M on I. Oops. So this is now the formula we use to design beam members. So hopefully by now, some of you have not quite finished your projects, but you've done enough to know how to design members carrying axial tension and compression. You calculate the axial forces. In terms of tension, you turn it into a stress. You get a stress and you compare it to yield stress, or you use the buckling formula for buckling. For bending, you calculate a maximum moment, and you calculate the stress at the top and the bottom, and you ensure it's less than the yield stress. So, as I said, using the formula, the first thing you have to do is draw your bending moment diagram to find where your moment is maximum, and that corresponds to where your shear force is 0. Because, as you all know, B is equal to dm dx. B is the slope of your bending moment diagram. So when your shear force is 0, your bending moment must be 0. Maximum, sorry. Did I say that right? You know what I'm talking about. Your slope is 0. and thus it means that there's a maximum value there. So we then put our maximum m into our equation, we work out our y value, our I value, and thus our maximum stresses occur at the top and bottom of the beam. So let's now do a problem. But I think before we do the problem, I need to point out what's plus and what's minus. Once again, tension we refer to as positive, compression negative. So when we use this formula, we don't bother, we don't think of y as having plus or minus values, we just calculate the stress. We look at how it bends and we go, oh, there's squashing in the top, that's compression. So don't bother defining y to be plus or minus. This is what I thought I had to point out. Finally, unit consistency. It's a formula, just as the buckling formula. The PL on AE is equal to deflection formula. You just need to be consistent. My favourite units, newtons and meters, millimetres. They're my favourite units because stresses are normally of the order of megapascals. So if you work in megapascal, which is a newton per millimetre squared, y has the order of millimetres, which is handy because our beams are normally a certain depth in terms of millimetres. So my member here, that's about 150 mil deep, so y would be 75. If I had to convert it to metres, it would be, that's 0.075 metres. You may make a mistake getting the decimal place in the wrong spot. So millimetres are the thing to use. When we work out I, we usually work in millimetres to the fourth. So the thing you have to be aware of is when we draw our bending moment diagrams, we work in kilonewton metre. So how do we convert what is 1 kilonewton metre in terms of newton millimetres? 1 kilonewton is how many newtons? Well, it's 1,000 newtons. 1 metre is how many millimetres? It's 1,000 millimetres. So that's 1 kilonewton metre is 10 to the 6 newton millimetres. I shouldn't have to do that, but I do because that's where a lot of you go wrong. Okay, now we can do a problem. We're going to do some beam design now. We have a timber beam. It's supporting a brick wall, which is our UDL load here of 20 kilonewton per metre. And it also has a heater in the middle that weighs 50 tonnes. So we are going to apply our heater as our point load. And our brick wall is our UDL load. Is our beam strong enough? So we're not doing a serviceability limit state, we're not checking how much it deflects, we're just doing a strength check. And we know the yield stress of timber, 15 MPa. Now, to do this problem, we need a value for I, which I will talk about on Wednesday. But when you have a rectangular beam of width B and of depth D, when you consider bending about the horizontal axis, the I value here is BD cubed on 12. So that's something you need to memorise, something you need to be familiar with. Now I've said here bending about the XX axis. We define an axis of bending as being the axis that divides the area in compression from tension. So the way I have this loading shown here, will I have compression in the top half of the beam or tension? I'll have compression here, and in the bottom half I'll have tension. So the axis of bending divides the compression from the tension region. So the axis of bending will be a horizontal axis. Okay? Okay, so doing this problem here, the first thing we need to do is draw our bending moment diagram. So in order to do this, we need to calculate our reactions. So let's take moments at A. Again, we're going back to basics. Our moment is 50 kilonewtons times 2.5 metres. It's anti-clockwise. No, it's clockwise, so it's negative. Then we have our UDL load, 20 kilonewtons per metre. It's acting over 6 metres. And when I position it as an equivalent point load, I position it in the middle at 3 metres. And that's also causing clockwise rotation. And I didn't draw my BY in here, so I will now. So now I have a free body diagram. So here I would then say plus 6 times BY equals 0, because my free body diagram is a stable structure, so it's in equilibrium. So from this, one would get BY equal to 80.83 kilonewton, and thus when you look at forces in the y direction, AY plus BY minus 50 minus our UDL load equals 0. So from that, we have a value of AY. So could everyone quickly try drawing that shear force diagram and bending moment diagram? So you haven't done the problem set questions yet, so you won't find this easy yet, but shear force, start at the left-hand side, follow the loads. And while you're doing that, I will just work out my moment of inertia. B is 220 mil, T is the depth, so hopefully you stepped up 89, and then the load started reducing by 20 kilonewtons per metre. So every metre you move up, it drops by 20. So that, after 2.5 metres, brings it down a value 39.17. And then we have a sudden drop here, equal to 50 kilonewtons. It brings it to a value of 10. And then I should have the same slope. How do I know I have the same slope? Because as well as B being equal to dm dx, W is equal to dv dx. That means the slope of this line here is equal to 20 kilonewton per metre. So that would bring me down to a value of 80, and then my reaction, thank goodness, is equal to that value, so I end up at 0. So there's my shear force diagram. So, bending moment diagram. Where do we know our moments are equal to 0? At the pin end and the roller end support. Value of 0 here, a value of 0 here. A positive shear force diagram, according to my relationship V is equal to dm dx, means the slope of my bending moment is downwards. Why is it downwards? Positive is upwards. Remember, we draw positive down. Because we're using the sign convention, we draw it on the tension side of the beam. A negative shear force through here, our slope is up. Those two lines are linear, my bending moment is a parabola, but it's not going to be a smooth parabola, because have a look, I have a value of 39 and a value of minus 10. That means the slope of my bending moment suddenly goes from 39 to minus 10. So there will be, I'm going to try and draw it with an obvious kink in there and make it look like a parabola all at the same time. Excuse the static. So it looks like so. So what is this a combination of? This is a combination of a UDL load and a point load. So if you draw those two bending moment diagrams separately, you'll end up with that. I'll leave you to do that. Now that value of the moment there is the moment we need, because to calculate the stress we need the maximum moment. So the most basic way is to therefore then cut the beam at 2.5 metres and actually calculate the value of the moment there. But you guys don't like doing it the most basic way. You like doing it the quickest way, and that is to calculate that area in here. So hopefully you can all work out the area of a trapezoid. So it would be the average height, 39.17 plus 89.17 divided by 2 times the width of 2.5 metres, and that will give me a maximum moment of 160.425 kilonewton metres. So looking at our stress formula, we know our maximum moment is 160. What is y? Remember, y is the distance from the neutral axis. Because if I was to draw the stress distribution, now normally when we draw the stress distribution, we draw it related to the cross-sectional area. So we draw it like so. But the stress distribution on that cross-section is actually coming out of the page, because my beam is coming out of the page. So my beam's sticking out like that, and it's bending like so. So rather than draw a big depth of beam in here and have to draw the whole 6 metres long and draw that in, we just automatically draw it relative to the cross-sectional area. Is that okay with everyone? Okay, so, I have to go back. And I haven't got room, don't go yet. I'm just going to put another blank page in. Oh, no, I can use the one before. Okay, hang on. I'll move that here. Good. Okay, so we just have to use our bending stress formula. So, stress is my on I. M we said was 160. Now, the units of M was kilonewton metres. And I said I want to work in Newton millimetres. So there's a 10 to 6 factor. My beam here is 700 deep. So what is Y max? Because in this formula here we want to know what stress max is. Well, that's equal to 350 MPa. No, millimetres. So multiply by 350 millimetres. And while you were working on the other question, I simply plugged in BD cubed on 12 here and calculated an I value. And that, lo and behold, gives me a stress of 8.9, which is less than 15. So therefore we can conclude that our beam is safe. Okay? It's sufficient to carry the load. Any questions? Is that a hand up or a stretch? No, that's him talking to someone else. Give me a couple more slides and then I'll let you go. Okay. This is a problem that's already on here, so you don't have to write it down. This time around, we have a bridge. It's made of an RHS, a rectangular hollow section. In your truss project, you used SHS, square hollow sections. It's used to support 2-point loads. Is the strength of the bridge adequate? So once again, you would have to draw a bending moment diagram. But just to note, in calculating I here, I said for a rectangle, a solid rectangle, it's BD cubed on 12. So for a hollow rectangle, you would calculate the outer area BD cubed on 12 and take away the inner BD cubed on 12. Just as if I asked you to calculate that area of the section, you would say the outside area, take away the inside area. We calculate I the same way. Shh, come on, I've got to 4:55. Give me to 4:56. Come on, let me just, this is all on here. You don't have to write anything down. Just let me ramble. Okay, so here, you would calculate the reactions, draw your bending shear force diagram, draw your bending moment diagram. So which moment will you use to calculate your maximum stress? The 80 kilonewton metres. So the maximum stress occurs at B, and based on our section being 350 deep, our Y max value here is equal to 150. Okay, go. And be rude to someone else. I'll see you all on Wednesday.